everyone, welcome to the Advanced Computer Architecture course. I am Dept, a PhD scholar in the Department of Computer Science and Engineering, IIT Guwahati. I work under the supervision of Dr. John Jose, and my research area of interest is multi-core architecture with special focus on prefetching and compression. This is the first video lecture on gem5 sessions, and we have planned 2 other such videos. The first session is an introductory session on the gem5 simulator, while the second and the third deals with core optimization and memory optimization. So with this, I start today's session. Gem5 is a full system simulator that is extensively used by the computer architecture community. This is because Gem5 simulates a real hardware where one can adopt any modifications for experimental purpose. The need for such a modification also arises from the fact that fabricating all modifications on a real hardware is not actually possible. This is because the fabrication cost is too high and also quite time consuming. Due to this reason, an architectural simulator such as Gem5 is used for the experimental purpose. This is the outline of today's presentation. I will introduce to the readers the full system simulator, that is Gem5, followed by how it works. Then I will show you how to configure and build Gem5 in your system. I will also show the real benchmarks that can also be used for evaluating the system performance in Gem5. Finally, I will explain the output statistics that are generated from the simulated machine. Gem5 is an amalgamation of M5 and GEMS. M5 is built by University of Michigan with multiple CPU models and instruction set architectures. It also has a classic memory model. The CPU and memory in M5 interacts with each other as master and slave using the available M5 ports. On the other hand, GEMS is built by University of Wisconsin with Ruby memory model, and it also has a flexible interconnection backbone, that is Garnet 2.0. It also models different types of coherence protocols. In the previous slide, as I have shown, the CPU models available in Gem5 will be described in details in the second video of Gem5, while the memory models will be described in the third lecture of Gem5. Gem5 is a modular discrete event driven simulator. That is, all the actions in the system are represented as events that are time stamped. The events are stored in an event queue and a time is attached with an event. As per the time, an event gets scheduled. For example, let us suppose that this is an event queue and a core request for an address A. The request is processed as an event that is entered into the event queue. Assuming that the current clock cycle is 1, the event is time stamped with 1. As the event gets dequeued, the normal procedure is whenever a core generates an address, it is initially searched in the L1 cache. Hence, searching in the L1 cache is another event, and that is time stamped with clock cycle 2, and that is entered into the event queue. If the L1 cache access turns out to be a hit in the cache, the L1 cache controller sends the block back to the core. This is then generates another event which is known as a reply event with timestamp 2. This event is also inserted into the event queue. Kindly note that this is a representative example to describe an event driven simulation, and this is how the simulation occurs in Gem5. Gem5 is also known as a full system simulator. By full system simulation, I mean it executes both user level codes and kernel codes, and hence models a complete system including devices and operating system. Gem5 also operates on SE mode, or this is also known as syscall emulation mode. In SE mode, it emulates most of the system level services, that is kernel codes, and just executes the user code. Hence, this mode does not model any operating system or any devices. Gem5 simulates a machine which we call as simulated machine, and the machine on which Gem5 is running is known as the host machine. Remember the term host machine and simulated machine, as I will use these two terms throughout the video lecture. Gem5 is written in C++ and Python, and all the operations and experiments are performed on the simulated machine. The figure shows a diagram of how Gem5 builds a simulated machine. On installing Gem5 on a host machine, it takes an input parameter. This input parameter is actually a simulation script which is written in Python. This script contains configuration of the simulated machine that is to be built by Gem5. Few such input simulation scripts are present in this path. One such script is ac.py and the next one is fs.py. I will explain more about the simulation scripts in the next slide. Gem5 on taking the input generates and builds a simulated machine. The behavior of the simulated machine can be observed as an output file in the m5 out directory inside Gem5. The behavior of this machine is implemented in C++. As I have already mentioned that Gem5 simulator takes a simulation script which is written in Python as input, that is ac.py, and the simulated machine's behavior is written in C++. Now, coming to the simulation script, the Python script ac.py contains two parts. The first part is configuration phase. This says what is the configuration of the simulated machine, and the next phase is simulation phase. This phase mentions how to build the machine. The configuration from the Python script are then converted into C++ structures through sim objects, and these are then passed to the C++ objects which models the system behavior. These sim objects generally represent some physical components such as cache, main memory or DRAM. All these components are represented using different sim objects. I will explain the whole procedure in greater details in the subsequent slides. Now, moving forward, Gem5 operates on two modes, AC mode and full system mode. Gem5 broadly simulates two CPU models, in order CPU and out of order CPU, and it has two memory models, classic memory and Ruby memory. Gem5 has two interconnection networks, simple and garnet. In this course, we will mostly handle with CPU models and memory models. Throughout our assignment, we will use the system emulation mode or SE mode. We will use both the CPU models in order as well as out of order, which I will explain in greater details in the second video lecture of Gem5, and we will use Ruby memory model along with the garnet interconnection networks. Gem5 is dependent on few packages. First, Gem5 can be installed in different platforms. It can be installed in Linux, BSD, Mac OS, Solaris, and it is dependent on the following packages: Git or Mercurial. This is used to clone or download Gem5. The G++ or GCC compiler is used to build the C++ system files. Python is required to interpret the simulation scripts, and Scon is required to build the complete Gem5 simulator. And finally, Swig, M4 and JLib are the extra packages that are required by Gem5 for installation. Now, let us see how do we configure Gem5 in our system. These are the commands. To install the dependencies, type the following command in the terminal: I will use an Ubuntu system to show a demo. You can download gem5 using this command. We can then build gem5 using this command, and to run gem5 we will use this command. I will explain the build and run command in greater details. This is the build command, where the instruction set architecture used is alpha. Throughout our simulations and assignment, we will use the alpha instruction set architecture. So, this is the simulated machines instruction set architecture, and in gem5 there are several other ISS available, that is alpha, ARM, x86, MIPS, null, Spark and PowerPC. gem5.opt is the binary that is commonly used during working with gem5. It is fast and it has almost all of the debug features. There are other types of binaries available, such as perf, prof, fast and gem5.debug. Next, -J9, this 9 indicates the number of cores or threads in the system plus 1. For Ubuntu users, you can type this command to check the number of cores that you have in your system. After building gem5, you will notice that inside the gem5 directory, a new directory named build is automatically generated. Now, we will run gem5 using the following command. Now, I will show a demo of the complete process that is to be carried out in your system. To build the gem5 system, we will type sconce build. We will use the alpha architecture and gem5.opt binary, and the number of cores that I have in my system is 8. So, I will use 8 plus 1, that is 9 as the number of threads in my system. This process requires quite a time, around 10 minutes to perform the complete building of gem5. So, at this stage you can see that the gem5.opt binary has been created. If you look inside the folder, you will find that inside gem5 a build directory is built. Inside the build directory, you will find the alpha architecture that has been built using the sconce command. Now, we will run a hello program in the gem5 build directory. So, for this we will type this command. Here the gem5.opt is the gem5 binary. The simulation script that we use is ac.py, and the options for the simulation script can be found by typing this command in the terminal. And -c provides the option for this simulation script. This can be any C code or this can be also any real benchmark. So, after a successful run, you will find this as the output. This is a hello world program, and if this hello world prints, it means the run was successful. You can also notice here is that it shows an entering event queue. This I have already explained that since gem5 is an event driven simulator, it has an event queue where all the events are queued and dequeued as the simulation proceeds. This line indicates that the first event was queued in the event queue at timestamp 0. So, now coming to the output of the simulated machine, it can be found in the gem5/m5out directory. Next, I will discuss about the output of the target machine. Text file contains the statistics of the output files inside m5out directory. The config.ini contains the machine configuration of the simulated machine. The config.json is same as the config.ini, but it is in JSON format. So, in stats.txt file looks somewhat like this. Here you can see that there is a sim seconds and something known as the host seconds. Sim seconds means that for how much time did the program hello world run in the simulated machine, while host second means that for how much time gem5 took to run in the host machine, that is your machine. This figure summarizes the complete procedure of how gem5 works. First, the input parameters that are given to the gem5 simulator, that is ac.py, in the previous slide are parsed by Python interpreters. These parameters are then passed on different sim objects as mentioned. Each of these sim objects represents one physical quantity. This may represent cache, the second sim object may represent DRAM, the next one sim object 3 may represent network, and so on. These sim objects are also written in Python file. So, we require a Python interpreter. For example, in cache implementation in Ruby, it has a sim object known as rubycache.py. Next, the C++ objects which define the system behavior, that is cache organization implementation of the cache, inherits the values from the sim objects. And finally, the system is built using GCC or G++ compiler, and the output of the simulated machine can be found in stats.txt, and the configurations that we used for the simulated machine can be seen in config.ini file and config.json file. Now, along with running user programs, one can also run real benchmarks to verify the behavior of a simulated machine with respect to the real world programs. There are two types of benchmarks, multi-programmed and multi-threaded benchmarks. In multi-threaded benchmarks, thread of an application spawns across multiple cores. Parsec and Splash are two such benchmarks. On the other hand, in multi-program benchmarks, separate applications runs on each core, like in Spec CPU 2006 benchmark suite. We will use this benchmark throughout the gem5 assignments provided in the course. So, next we go through a quick directory tour of gem5. Inside the gem5 directory, you will find these directories. Build contains the build directory, which is generated after typing the scons build command. The build OPT hold files that define default settings for build different building configurations. This folder contains simulation configurations. This contains gem5 dependency, but this is not a part of actual gem5. This directory contains include files that are used to simulate and compile gem5. The output files are present in this folder, and source contains all the gem5 implementations like caches, cores, CPU models, interconnection models, and everything. This directory contains low level softwares like firmware or bootloaders in simulated system. This directory contains files related to gem5 regression test, while this directory contains utility scripts or programs and useful files. We will mostly deal with this folder and the config folders. All the references are mentioned in the slide.
In this video, I will discuss the gem5 installation, the version which is compatible to both Ubuntu 18 and Ubuntu 20. To be able to correctly run gem5 on Ubuntu 18 or Ubuntu 20, we need gem5 version 19 which is compatible with both, and we can download it from the given link. So as you can see the link, and we can just copy paste into our browser, and we will be able to download a zip file of gem5 version 19 repo. So you just need to unzip that gem5 and you will be able to get gem5 directory, and later on you need to install a compatible scones version which is 2.5.1 from the given link. If there is a default scones version already installed on your system, you can just remove it using sudo apt get remove scones, and then you can download it from this given link. Same way we will just copy paste it into the browser, and then we will be able to download the scones directory into our system. So as you can see, I had downloaded the required versions of gem5 and scones into my system. So now we can proceed to install all the dependencies to be able to build gem5 correctly. So before that, to be on safe side, we will just issue a command sudo apt get update. This command will update all the repositories database, and we will be able to download all the dependencies correctly. So after this, we can proceed to install all the dependencies required to build gem5. So these dependencies are m4, swig, python 2 developer version, then build essential, and then zlib1g developer version. So we just need to complete the installation. Now we can proceed to install the scones that we had already downloaded. So for that we need to move into scones directory, and there is a readme.txt file. From there you can get the installation instruction, and we need to install it using Python and as a standard library. So we will issue the command here, python setup.py. So first we need to move into the scones directory, then python setup.py install standard lib. So here you can see python not found error is coming. This is because the default version of Python is not the version which can be used to build this version of scones. So we basically need Python 2.7 version to install scones in our system. For that we need to set Python 2 as default Python, and you won't be able to install scones or build gem5 using Python 3 version. This is only compatible with Python 2 version. So for setting Python 2 as our default Python, we can use the command sudo update hyphen alternatives hyphen install slash user slash bin slash Python. So this is the path where the Python is installed. And then we need to mention for which we need to update our alternatives. Then Python, then again the path of the Python 2.7 version, which we actually need to set as default. So after this we can check now the default version of Python which is installed in our system by issuing command python minus capital V. So now 2.7.18 is the default version. If you don't have this version of Python, you need to issue this command first. So now we will install scons using the same command python setup.py install standard lib. So you need to install it as a root user, so you need to mention sudo here, then it will get installed correctly. Now we can check the scons version 2.5.1 is correctly installed on our system. So now we can proceed to build gem5. So we need to move into gem5 directory and then we can issue a command scons build slash the architecture name alpha, then gem5.opt minus j and a number which mentions number of CPUs in your system plus 1. So here we are getting an error, no module named 6. So you may or may not get this error. So in case if you get this error, we need to install this module named 6. So you can just install this module using command sudo apt-get install python-6. So I had already installed. Let us issue the same command for building gem5 scons build slash architecture name slash gem5.opt, and at the end we can also mention minus j option with a number which is number of CPUs plus 1. If you have 4 CPUs, then you can issue minus j5. So this process will take some time. So as you can see here, we had successfully built gem5. So on my system it hadn't took much time because I had already built this, but on your system it might take near about 45 minutes. So now let us try to run a workload on our simulated alpha architecture. So we have set of workloads inside binaries directory, which is inside a gem5 directory. So these workloads are basically CPU 2006 benchmarks which can be used to measure the performance of our simulated architecture. Here we will try to execute one benchmark using the command build slash alpha slash gem5.opt. Then we will use a script named se.py for system emulation mode, which is inside configs slash example slash the name of the file. Then we can mention the benchmark name with -bench is equal to NAMD is the name of benchmark. Then number of CPU is equal to 1, CPU type is equal to atomic simple CPU, and number of instruction we are simulating is 1 million. So you can see we had successfully executed this workload for 1 million instructions. Sometimes you can face error workload not found while executing a workload from the binaries. So this error is basically due to the wrong path which are set in benchmark execution file. What you need to do to correct that error is to change the path according to your directory path. So we have a binaries folder inside gem5, so in which there is a CPU 2006 directory which is storing all the benchmark files. So we can just copy the path of that directory, and in the benchmark execution file CPU 2006.py we can change the path of all the benchmarks. So here we are mentioning the path of those benchmark files. So here we need to make some changes. So we can just replace this path with our actual path. So we can replace all because there are multiple instances of same string being used inside this benchmark execution file. So you can replace all, and then you can save that and again try to run the benchmark workloads. So if you were getting workload not found error, then you can try to change the path into the correct one and you will be able to successfully run those benchmark workloads. I hope now you will be able to successfully build gem5 on your respected version of Ubuntu system. Thank you.